Okay, today we're going to be talking about the complex plane. So, we know that in with real numbers, we can represent them along the number line. 0, 1, 2, so on and so forth. Then you've got the minus numbers, so on and so forth. But we can't do that with complex numbers. We need to use a plane rather than a line. So the plane that we used, complex plane, was accredited to a mathematician called Jean-Robert Argrand, and so we use what's known as Argrand diagrams. So say we've got a complex number x plus iy, we represent x and y as Cartesian coordinates. So, for example, say we had, let's do z1 is equal to 2 plus 3i, and we've got z2 equal to 5 minus 3i. So this would be our Argrand diagram for these coordinates. So we would plot along the x-axis our real component for z, and along our y-coordinate we plot the imaginary component of x. So for z1 we'll have point A, and we'll have that as 2, 3. And for z2 we're going to have point B, which is going to be 5 minus 3. So let's have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. So our point A is going to be 2, 3, this is point A, and our point B is 5 minus 3, which is, that's a terrible 3 there, 5 minus 3, which is down here. Now, we can easily see from this that we can now, let's get a different colour, plot on this a vector OA and OB. So we now have position vectors. We have OA is equal to 2, 3, and we have OB is equal to 5 minus 3. Now, this is going to lead us into a whole new way of representing complex numbers. So we're going to look at 3 different ways of representing a complex number. So the first way is what we've been doing, is called the Cartesian form. The Cartesian form is when we just have x plus I, y. So this is the Cartesian form. Now the second way is called the modulus-argument form. This is the second way of representing a complex number. So to begin with, we need to define what is the modulus and what is the argument of a complex number. So let's say we have z equals x plus iy with position vector xy, then the modulus of x plus iy is going to be x squared plus y squared, just what we were doing with our vectors. And so the notation that we give this, so the modulus is defined as this. This is the notation for modulus. And the plural of modulus is moduli. So let's use our Argrand diagram just to plot what this would look like. So we've got our point here, and here's our position vector, and this here is our value of x along here, and this is our value of y. And then we're going to have some angle theta. So this is our real z and our imaginary z. So we take our x and y from the Cartesian form, and now we have our value of the modulus, which is going to give us the length here. So this is going to be our modulus of z, and now we need to define the argument. So the argument of a complex number is the direction of the position vector. So this theta. However, we need to define it a bit more clearly than that. It's the angle between the positive real axis and the position vector. So this is we call that angle the principal argument. Theta of a complex number is an angle such that minus pi is less than theta is less than or equal to pi. So theta is going to be between minus pi and pi. Sometimes it might be more convenient to give theta in terms of, so sometimes theta is defined as 0 less than or equal to pi less than 2 pi. And theta is in radians normally. So if we have z equals x plus iy, then the argument of z is this is the notation for the argument of z. And therefore, we can see from here, we can use trigonometry that tan theta is going to be y over x. Now, when you're asked to find the argument of z, it's really helpful to do the Argrand diagram, because it will show you where theta is, and it will help you to define to make sure you get the right value of the angle. Now we're going to do a number of exercises just to show what I mean by that, and yeah, just to pay attention to where is the position vector, and therefore what angle are we looking at. So we're going to find the modulus and argument of the following. So we've got 5 plus 12i, we've got minus 3 plus 4i, we've got 12 minus 5i, and we've got minus 4 minus 3i. So let's do the first one. So let's first begin with drawing our Argrand diagram for the first one. So we're going to have 5, 12. So this is going to be 5, and we've got 12 here, and we've got this here, and we've got theta here. So this is 12, and this is 5. So the modulus of 5 plus 12i is going to be 5 squared plus 12 squared and the square root, which comes out at square root of 169, which is 13. Now, the argument of 5 plus 12i is going to be the inverse tangent of y over x which comes out at 1.176. So just round it to 1.18 to 3 significant figures. So let's now do the next one. So z in this case is minus 3 plus 4i, and again we do our Argrand diagram. So it's now minus 3 and 4, so about here. So this is minus 3 and this is 4. So we can find our modulus of minus 3 plus 4i is going to be minus 3 squared plus 4 squared, which comes out at 25, and the square root of 25 is 5. So this is 5. Now, when we find theta this time, so we're going to get this angle here, which is alpha, we'll call alpha, we'll call it alpha. So the tan of alpha is going to be 4 over minus 3. However, we want to, this is our definition of theta, is the angle that the position vector makes with the positive real axis. So it's this bit here, this is theta. So theta is going to be pi minus, so pi is going to be this minus alpha. So it's going to be pi minus the inverse tangent of 4 over 3, sorry, it's going to be the size of 3, which comes out at 2.214. Now our final one, that's not our final one, 12 minus 5i. This is z equals this. So again, do our Argrand diagram. So 12 minus 5 about here. It's not important, the accuracy is not as important as getting the position. And then that's going to be minus 5. Or 5. Here's our minus 5. Okay, so Again, do the modulus first, that's the nice easy bit. And that comes out at root 169, which again is 13. Now, theta is going to be equal to minus alpha. So this here is the angle that we have, and this is going to be we get this angle, but we want this is going to be a negative angle. So the argument of 12 minus 5i is going to be minus, because we're taking the minus of the inverse tangent of y, which is 5 over 12, which is going to become minus 0.395. So when you're in this quadrant, theta is going to be minus alpha. So bear in mind how the argument works in the different quadrants of the Argrand diagram. So finally, z is equal to minus 4 minus 3i. So this is the final quadrant, so it's going to be minus 4. This is minus 4 and minus 3. So it's going to be about here. And so we've got our, again we're going to have an angle here, alpha. So first let's find the modulus. So it's going to be 4 squared plus minus 3 squared, which comes out at root 25, which is 5. And now theta is the angle that the position vector makes with the real axis. So it's this value here, the positive real axis. This is our theta. So theta this time is going to be minus pi plus alpha. So it's going to be minus pi plus, and alpha is going to be the inverse tangent of this bit here's 3, and this length here's 4, which comes out at minus 2.50. And remember, these are all in radians. Okay, so we've defined the modulus and the argument. So now we're going to go and actually define the modulus argument form of our complex number. So let's just draw some just basic complex number here. So we've got, this is y, this is x, this is theta, and here's r. So from our trigonometry, cos theta is equal to, so remember we get the x and y values from the Cartesian form of the complex number. So this is z equals x plus iy. So cos theta here would be equal to x over r, and sine theta would be equal to x over r. Therefore, x, our value for x, can be written as r cos theta, and y can be, that's wrong. That's y, sorry. so x, y is equal to r sine theta. So if we've got z equals x plus iy, we can then substitute our values x and y for what we've got here. X now equals r cos theta plus I r sine theta, and we can rearrange, tidy that up a bit, take the r out, and just have cos theta plus I sine theta, where r is the modulus of z and theta is the argument of z, which we've just been defining. So this here is what we call the modulus argument form of the complex number. Okay, so let's take an example. So we've got two complex numbers. U is 6 minus 3i and w is minus 7 plus 5i. And we want to write both of them, u and w, in the modulus argument form. So let's take u first, and we know the modulus of u is going to be, which is going to be equal to r, is going to be 6 squared plus minus 3 squared, which comes at the root of 45, which simplifies down to 3 root 5. Now we can do our little Argrand diagram. 6 minus 3, so this is 3, this is 6. So it's in this quadrant, so this will be alpha. So theta is going to be equal to minus alpha, which is going to be minus the tangent, the inverse tangent of 3 over 6, which comes out at minus 0.464 radians. So now we can rewrite u as 3 root 5 cos minus 0.464 plus I sine minus 0.464, and that's our value, that's u in the modulus argument form. Now let's do w. It's minus 7 plus 5i. So r is going to be the modulus of w, minus 7 squared plus 5 squared, comes out at the square root of 74. And we'll just leave it as the square root of 74 because it's not going to simplify down nicely. Let's draw this. So we've got minus 7, 5 here. So we've got 5, 7, and this is going to be our value for alpha. So this time theta is equal to, remember theta is this one, is going to be pi minus alpha. So it's going to be pi minus the tangent, inverse tangent of 5 over 7, and that comes out at 2.52. So now we can rewrite w in the modulus argument form. So we have our r, then we have our cos 2.52 plus I sine 2.52, and that's our modulus argument form. Now, that brings us to our final way of writing complex numbers, and this is the exponential form. So, Euler, who is in the 18th century, oh dear me, what a mess I'm writing with this, 1783, so in the 18th century, he discovered that the modulus, this part of the modulus argument, so cos theta plus I sine theta, is actually the same as e to the I theta. So this enables us to write z, if z is r cos theta plus I sine theta, we can rewrite z as just being r e to the I theta. And this here is the exponential form. So the coordinates r and theta, where r is the modulus and theta is the argument, are called polar coordinates. So when we have the modulus argument form and the exponential form, we're dealing with r and theta. So we're dealing with the complex number in its polar forms. These are the two polar forms. But when we just have z equals x plus iy, we've got the Cartesian form and we've got Cartesian coordinates. So let's do some examples. So we have z1 equals 1 plus I, and we want to write it in the argument form and the exponential form. So first thing to do is let's just draw our little Argrand diagram. It's a nice easy one. It's just going to be up here, this will be theta, this is 1, this is 1. So the modulus of z1 is just going to be 1 squared plus 1 squared, which is root 2. So r is going to be root 2. And the argument of 1 plus I is just going to be the inverse tan of 1, which is pi over 4. So the modulus argument form, z1 is going to be r, which is root 2, cos pi over 4 plus I sine pi over 4. And our exponential form of z1 is going to be root 2 e to the I pi over 4. Next, let's take z2, and this one's in the exponential form, and we want to, no, it's not 2, it's a 3. We want to write it in the argument, the modulus argument form and the Cartesian form. So this is nice and easy. So here we've got r is 5 and theta is pi over 3. So z2 is just going to be 5 cos pi over 3 plus I sine pi over 3. So now we can draw an Argrand diagram, but this time we've got theta. We know theta is pi over 3, and we know that the modulus is 5. So here we need to find the values of x and y. So x is going to be 5 cos pi over 3, and y is going to be 5 sine pi over 3. And you can see it by actually equating the values in our argument modulus form. So this would be, x is going to be 5 over 2, and y is going to be 5 root 3 over 2. So z is going to become 5 over 2 plus I 5 root 3 over 2. Let's do one more of these. So now we've got z3, and we're going to have this given in the modulus argument form. Cos pi over 12 plus I pi over 12. I want to write it as exponential and the Cartesian. So again, reading it off, just r is going to be 2, theta is going to be pi over 12. So z3 can be written in the exponential form really easily. So it's going to be 2 e to the I pi over 12. And again, just using the same way as we did previously. So we know that something like this, we've got 2, we've got pi over 12, and now this is going to be y and this is going to be x. So x is going to be 2 cos pi over 12, which comes out at root 6 plus root 2 over 2, and y is going to be 2 sine pi over 12, which is going to be root 6 minus root 2 over 2. And that gives us z3 is equal to root 6 plus root 2 over 2 plus I root 6 plus root 2 over 2. Okay, now what we find is the exponential form of a complex number is useful for multiplying and dividing complex numbers, and that makes sense because we can just use our rules of indices. So let's have u is 5e to the 2i, and w is 10e to the minus 3i. So we want to find the modulus and argument of u times w and w over u. And we want to then show u, w, uw and w over u on an Argrand diagram. So uw is just 5e to the 2i times 10e to the minus 3i. So that's just going to give us 5 times 10 is 50. Then then we can use our laws of indices here. 2i minus 3i, which is going to give us 50 e to the minus I. Now w over u is going to be 10e to the minus 3i over 5e to the 2i, which comes out 10 divided by 5, is 2. Then we're going to have minus 3i, then minus 2i, So it's going to be 2e to the minus 5i. Now, remember, we had this condition that theta had to be between minus pi and pi. Here, we've got minus 5. So minus 5 is less than pi, which doesn't satisfy this condition. So this tells us that this value for that theta is not the principal argument. So we need to take our theta is going to be equal to 2 pi minus 5, because we've got this angle here, is alpha, this value 5, but we want this value here, theta. Okay, so we can then take this value for our theta, so w over u is going to be, our value of r is 2, e, and now it's going to be 2 pi minus 5 I. So this is one of these ones you need to be just really careful with your value of theta. Now, we're going to put all these on an Argrand diagram. So, firstly, our value of u is going to be it's 5 cos 2 plus I sine 2. If we work those values out, we get minus 2.08 plus 4.55i. So our first coordinate is our first point on the position vector for the Argrand diagram will be A is minus, we'll just make minus 2, 4.5 roughly. W is going to be 10 cos minus 3 plus I sine minus 3. That theta should not be there, because 2 is the value of theta. Calculating that, you'll get minus 10, minus 9.90 minus 1.41i. So our second point B will be, we'll call it minus 10 minus 1.5. So when you're doing these, you're finding out the Cartesian coordinates, you're kind of just doing rounding it to the most sensible kind of number that you're going to be working with. So you're just going to use a bit of common sense. So UW is going to be 50 cos minus 1 plus I sine minus 1, which comes out at 27 minus 42.1i. It's going to just rethink here. So C is going to be 27 minus 42. And then W over U is going to be 2 cos 2 pi minus 5 plus I sine 2 pi minus 5. So so that comes out as 0.567 plus 1.92i. So our final point is going to be D, and it's going to be 0.52. So we've got all these coordinates. Sorry, it's a bit messy and we've not got much space. So A is -2, 4.5, so it's just going to be up here. Oops. B is going to be over here somewhere. C is way down here. And D is like here. So A, B, C, and D is kind of over here, so it's not very easy to see. I'm sorry about the scale. I've not got much room to make the scale look anything decent, but that gives you a kind of rough idea of what it would be like. Okay, so if we want to, say we have Z1 is R1 e to the I theta 1, Z2 is R2 e to the I theta 2, we can have some general rules. So if we wanted Z1, Z2, that is going to come out to R1, R2 e to the I theta 1 plus theta 2. If you had Z1 over Z2, oops, that comes out at R1 over R2 e to the I theta 1 minus theta 2, just the rules of indices. So these are two really useful identities, and it shows us that if you want the modulus of Z1, Z2 is going to be equal to the R1, R2, which is the modulus of Z1 times the modulus of Z2. And the argument of Z1, Z2 is going to be equal to theta 1 plus theta 2, which is just the arguments of Z1 plus the argument of Z2. Similarly, the modulus of Z1 divided by Z2 is going to be R1 over R2, which is just the Z1 divided by Z2, and the argument of Z1 divided by Z2 is going to be the argument of Z1 minus the argument of Z2. So, in the exponential form, to multiply two complex numbers we multiply the moduli and add the arguments. And to divide two complex numbers, we divide the moduli and subtract the arguments. Okay, so we're going to look at one more example. So we've got complex numbers u, which is 9 plus 12i, and we've got w, which is minus 5 minus 3i. I want to find the modulus and argument of UW and U over W. So let's start by just finding the modulus of U, which is going to be 9 squared plus 12 squared in the square root, which is square root of 225, which is 15, and the modulus of W, which is minus 5 squared plus minus 3 squared, which is the square root of 34. Okay, so for U, we have nine, and we have 12, we have some theta, and this is our modulus. So the argument of U is going to be the inverse tangent of 12 over 9, which is 0.927. And then we have minus 5 minus 3. So this is 5 and 3, and this will be alpha. So for this one, theta is going to be minus pi plus alpha, which is minus pi plus tangent of 3 over 5, which gives us minus 2.601. So we know, so we want the modulus of U times W, which is going to be the modulus of U times the modulus of W, which comes out at 15 times root 34, oops, let me just write that as 15 root 34. And we want the argument of UW, which is just going to be the argument of U plus the argument of W. So it's 0.927, and it's plus minus 2.601, which comes out at minus 1.67. And remember, this is in always in radians. And then we've got for the modulus for U over W, that is going to be the modulus of W over the modulus of W, which is 15 over root 34, which is, so what we would do to tidy this up, you would, because we don't want the third on the bottom, so we'd multiply it by root 34, so that gives us 15 root 34 over 34. And then we've got the argument of UW, and see this little trick here, this is something just to have tucked away to pull out whenever you have that situation where the third is on the bottom, just to tidy that up. Anyway, so the argument of U over W is going to be the argument of U minus the argument of W. So argument of U is 0.927 minus 2.601, which comes out at 3.528. However, pay attention, 3.528 is greater than pi. So we are in the situation where we need to, this is not the principal argument. So theta is going to be minus 2 pi minus 3.528, and that comes out at minus 2.75 to 3 significant figures. So again, in radians, and you give your answer to the 3 significant figures. So I hope that helps.